Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on Java native interface, and so far we have looked at how to get and set the fields of an object, a static field or instance field, regardless of whether it's a private or public in C++ when we are dealing with Java objects. And then now I want to talk about something that is sometimes it's important, especially if we want to have access if we want to access many fields of an object at the same time and manipulate them, and that's about caching the field IDs. So you see, so far we said that for the instance and static fields, we first need to get the J class of that object, right? And we ask JVM to look into the class path and find the class, and then returns us a pointer which points to the basically a class object in the meta space that is attached to this Java class. All right, so basically a J class is a pointer that points to the meta space. And then for if we want to access any field and manipulate fields, we have to also get the J field ID, right, using the get field ID or the get static field ID. And again, I'm going to put this inside this diamond bracket to say that this is optional depending on whether we are accessing a static field or an instance field. All right, and we always pass the J class, the name of the field, and then the signature of the field. If it's a primitive, it's ID for integer and double. If it's an object, then we pass the fully qualified name starting with L and ending with semicolon. All right, but then regardless of what instance of the object we pass in C++, we pass to C++, J class and the J field ID are always the same, right? Because these are not related to the instance of an object. These are related to the class itself. So these are related to the class. So we see that the J class and J field ID do not depend on the object instance. So J class and J field ID are meta information that are related to the class itself. These are class level information. And then we need to only evaluate them once, even for different instances of a class. So let's say I have a native method that I instantiate like 1000 instances of an object. Let's say the person object, I instantiate 1000 persons, and then write the for loop that goes through all these persons and invokes a native method on these persons, right? And then for each person, it sets the name to something and the age to something, right? But then inside that native method, the implementation in C++, inside the function, I have to, for each time that C++ function is called, it has to ask JVM to get the J class and the J field ID, right? Because we put this inside that function. And this has a quite a lot of overhead and penalty, because it takes time for the JVM to search the class path and tries to find the J class and then the field ID. But again, these two are not related to the instances of an object. These are class level. So we can somehow cache them such that the very first time that the C++ function is executed, these two values, the J class and the J field, are calculated. But in the subsequent calls of the function, these are not calculated anymore. These are not evaluated, right? So how do we do that? So there are two approaches here. One is method caching. Basically, we cache this J class and J field ID, directly cache them in the function itself. And C++ allows us to cache variable inside the function using the static keyword, right? So in the context of a local variable inside the function, the scope of a function, the static keyword means we are caching that value. So even if we go out of the scope and come back to the function again, the value of that variable, of that local variable, is still the same as before. So I have an example here. Let's say I define a function that takes an int value x and then calculates a value y, which is integer, which is equal to 2x. And I just print it to the console, right? Cout y and l. But then I use the keyword static here in front of the y. Now in the main, I have double x, which is 3, and then call this function 3 times. Func x plus 1, func x plus 2. So I'm effectively passing 3, 4, and 5 to this function. The very first time that I call this function and pass 3, this y gets evaluated to 6, and 6 is printed to the console. But because this is static, the next time I call this function with a value of 4, this line is not executed again. And then the 6, which was the previous value of this y variable, gets printed. All right. So because this line is a static variable, is defining a static variable, this variable gets initialized only once and never again. Okay. Because this is an initialization of this variable. We say define it and initialize it. But for any static variable, the initialization always happens only once, the very first time we call the function. All right. So in the entire lifetime of the program where we're using this function, the value of y is set by the very first parameter that we pass to the function, the very first call. All right. So this is the method caching. There is another way of caching. It's called global caching, and basically what we do here is that we define global variables in the CPP file that are the J class and J field ID. So we define these two as global variables in the CPP, the C++ file. And then what we do, we create a static method, typically private, inside the Java class, which is called init IDs. So this is a native. So this is a native method, a static native method, init IDs, and then we put it in a static initializer. So we know that the static initializer is loaded, is executed the very first time, and only one time when a class is loaded inside the memory, right? And because this is a native method, it executes in C++, and inside the code, inside the C++ function, we basically do this evaluation for the J class and the J field ID. All right. So this is another way. And the reason that we might want to do a global caching, because we may need to use this J class and J field ID in different functions of the C++ code, right? So it doesn't make sense to evaluate them in separate functions separately. So we can just globally define them and cache them, and then use them in as many functions as we want. So let's head to Eclipse and try to look at how this method caching works, and then look into a Java example, and then also look at the global caching. So here I'm going to, let's clean up a little bit. I'm in the C++ perspective. So let's create a .cpp file, which is a compilation file. Let's call it method caching. Actually, I forgot to add the CPP. So actually, let's because this is configured to create a native library, dynamic library. Let's create a new C++ project, and I'm calling test caching. All right, and let's set it to create a hello world, and then finish. All right. So right now this is inside my workspace, but not inside my basically working set. So I'm going to go to this triangle and click on the edit active working set, and then I'm going to search for the project that I just created, test caching, and add it to my working set. All right. Now it's visible inside my working set. And in the CPP, I have this test caching. All right. So first of all, let's compile and make sure that it compiles fine and creates an executable. And by default, the projects are set to create executables. The binary is executable. So this is working. This is working, right? So let's see what we mean by method caching. I'm going to define a function which returns an int. So func int. Let's say it returns void, right? It doesn't return anything. And let's say it takes an x, and then let's say it takes a y value, and then multiplies x by 2, and then do a cout y and end line. All right, so this is what happens, and then we create an int here, let's say x, which is 3, and then we call this function with x, we call this function with x plus 1, and then we call this function with x plus 2. So what do we expect here? We expect, okay, we're passing 3, so y becomes y is a local variable, so it gets generated, it gets created on the stack, and then is initialized. So this is basically initialization of y, right? This is not assignment, this is initialization, because when right exactly where we define this y, we also initialize it. All right, so this is not assignment, this is initialization of a variable. So let's run this. All right, so 6, 8, 10. So we pass 3, gets multiplied by 2, we get 6, and then 4, 8, and then 5, which is 10. All right, so what happens if I put a static here? Now this variable is a static, it's a local static variable. All right, and there are two things. One is that a static local variable means that if we go out of the scope and then we come back in the function again, this y value still retains its previous value, its last value, right? The other thing is that when we do a static variable, initialization by default, the way a static is defined, initialization only happens once in the entire lifetime of the program. So this y variable is a static, which means we can only initialize it once, right? So when I pass 3, it gets initialized to 6. When I pass 4, this y is already there with a value of 6, and it's not going to be initialized again. So it's not going to get the value of 8. So if I run this, I get 6, 6, 6. So effectively we are caching the value of y to the initial value, which is exactly what we want with this basically J class and J field ID. If we set them as a static variable inside the C++ function, the first time we call that function, these get initialized, right? Because this is definition and initialization. But the next time the function is called, these two expressions are not going to be evaluated, and we don't get the overhead of asking JVM to find the class on the class path and then find the ID of the field, right? So this caching helps a lot in terms of speeding up the process of retrieving the meta information. All right. So what happens if I basically initialize to 0 and then reassign it to 2 times x? So what happens here? Let's run this, and again, it's still a static. Does it compile? Yes. Yeah, now we get 6, 8, and 10. So what happened? Y was a static variable, but now its value is changing. 6, 8, and 10. Why? Because this expression is not initialization. This is assignment. And we can reassign a static variable, another value to a static variable. That's fine. So this is assignment, not initialization. Okay? Initialization means you define it and you give it a value. So y is always initialized to 0, and this expression gets executed only once in the entire lifetime of this function. No matter how many times we call it, this expression gets evaluated only the very first time, because this is initialization, and static variables only get initialized once, the very first time. But then we can do reassignment. All right. So if I run this again, as you can see, this works. All right. But if I basically put this back here and then compile again and then run this, you see we get 666. And again, I want to highlight the difference between initialization and assignment or reassignment. Okay. So this is basically the way we can deal with caching. And let's go back to Java, and then let's create a new package test10. and I'm going to create a class, basically person. All right, and again it has a string name and int age. And let's create a constructor, public person, a string name, and this dot name is name, and let's initialize age to 21. Okay, so basically let's try a class here, test caching or test method caching with the main method here. So in the main method I'm going to have test1, and basically test1 is just public static void test1. And then I'm going to have a method or native method, public native void set age, for example, and then passing a person object with an int age. Okay, and then I'm going to create a person array, persons or people, new person, 1000 persons, and then I'm going to say for int I equals 0, I less than people dot length I plus plus, basically set age. Okay, maybe let's put it in the code block. I call the native method, and in order to do that, because this is not static, I can make it a static, public static native, that's fine, set. So I say people I and I, right? So 1000 times I'm calling this, and let's time it. So basically long start is system dot get system time dot current time millis, and long end system dot current time millis, and then long duration basically end minus start, and sysout time millisecond is equal plus duration. All right, so let's see if caching helps with the speeding up this process. And remember, this set age is a native, so what we need to do here, let's go back to our C++ perspective. In this native C, we have the headers, and then I'm going to select my Java code, test method caching, and run the Java H tool, and it puts the header file in the header folder. So it's test10 here, and then let's create a CPP file method, let's call it caching, like field or maybe ID caching .cpp. So first we include the header file dot header test10. All right, and then copy paste the method, the function from the header file. This is the prototype, and we're going to implement it. So now here J class refers to the class that is calling. J object is our person, and J int is the age, right? And again, now you already know the drill. So we get the J class, that is a pointer to the meta space of the class of the person object, so person class. So we say that JVM find class, all right, and it's in test10 person, capital P person, and then J field ID, and we're going to say age ID is environment get field ID. This is not a static field, this is instance field. So we use the get field ID, we pass the J class, the name is age, and the signature is integer. Okay, and then what we're going to do here, we're going to ask the JVM to set the age. Environment set field, set int field, right? So this is a primitive set int field. We have to pass a J object reference because this is accessing or setting the instance field. The field ID is age ID, and the value is age. All right, so this is it. And again, each time we execute or call this method, this function from Java, these two expressions, basically getting the J class or defining the J class and then initializing it, defining the age ID and initializing, this happens each time. So let's compile this. This compiles fine. Let's copy and paste to our Java, this dynamic library, and go back to our test, and maybe let's give the person a to a string method. I just want to see the name to the age, okay? And then here basically we have to say we have to create the people. So people I is new person, let's call it Bob. All of them have the same name, or Bob plus I, maybe I is the ID. And then yeah, and then we send it to C++. All right, so we also need to load the dynamic library into memory. System dot load library native underscore C. All right, so this should run and execute fine. So it took 1 millisecond. Now obviously let's increase the number, 1 million. It took 591. Let's run it one more time. 611. Let's run it one more time. 616. So let's say 600 milliseconds, right? So with no caching, we got 600 milliseconds. Now how do we do the caching? We go here, we just put a static keyword at the beginning, static. So what happens? We are defining and initializing, and as we said, initialization only happens once, the very first time this function is called, because this is not assignment, this is definition and initialization, right? Initialization means you declare it and you assign a value to it. This becomes initialization. Assignment means you declare it and then assign some value to it. It already has some value and now you are assigning a new value to it. But static parameters, static values get initialized only once. So we are initially or effectively caching this J class and J field ID, these values. So if I execute this function 1 million times, these two expressions only get executed once, the first time. So let's compile this. It compiles fine. Let's copy and paste here. Okay. And then go back here and see if there's any difference. 150. Let's run it one more time. 148. Let's run it one more time. 150. So with method caching, or let's call it local caching, we went down to 150 milliseconds, which is basically a factor of 4, right? So a factor of 4 reduction in the time. And this is a very important and clever idea for you guys to understand that if I have a C++ function that does some stuff on an object, so on many objects, 1 million instances of an object, right? So if I want to access its meta information like J class, J field ID, it's best to cache them. Basically when I declare them, immediately I get the values and initialize these. And because these are static, initialization only happens once. So we already have some good amount of saving, which here was a factor of 4. And again, if I remove these static keywords, now these are not being cached. So each time we call these two variables, person class and age ID, are defined or declared and then initialized each time. And this puts an overhead on the JVM because it has to look for the class, look for the ID. Yeah. So if I compile this again and then copy and paste this, copy and paste the dynamic library, and then run this again. So did I copy and paste this? So if I compile this and then copy and paste the dynamic library and then run this again. All right, now it takes 630 milliseconds. Let's run it one more time. 600. Okay, so this is more or less an average number, 600 milliseconds. And then again, to double check, if I put the static keyword here and the static keyword, we only ask JVM once to find this JClass and JFILD. So let's compile this. Okay, and then copy and paste to Java. And then go back and run this. This should be around 150. Yes, 154. So we are definitely saving a factor of 4 for 1 million objects, which is a huge saving, of course. And yeah, I mean, if you are just operating on like 10, 100, or even 1000 objects, this difference might not be very important. But if we are operating on 1 million objects or more than that, this is very important to know that we can cache these IDs and only get them once. Now, the problem with this kind of method caching is that if I have multiple methods, so let's say I have also another native method, so public static native void set age person and a string name, right? Sorry, set name. So if I select this Java and run the JVM Java H again to update the header file, now I also have this file. And if I go back to my ID caching, so obviously the first parameter is environment JVM. The one is a JClass reference to the calling class. The next is the JObject person and the JString name. And now you see what happens. Again, I have to start from scratch, right? Do this initialization and get the JClass and the JField ID again, okay? So, and I can do that. And again, I can also use the static to gain some overhead, a factor of 4 improvement. So here we get the basically name ID, name, and it's a string. So L semicolon Java /lang/ string. And then we ask the JVM to set the name, set basically object field. Set object field. The J object is the person, the field ID is name ID, the value is a J object. In this case, it's a J string, which is name. Okay. So again, I'm going to remove the static ones. And then basically I'm going to compile this and then copy and paste the dynamic library. Okay, and now here I call the set age, and then before that I can also set the name, set name, basically people I and then James plus I. It doesn't matter. So let's run this. So it takes pretty much double. Before we had 600 milliseconds, now we have 1200 milliseconds because these two functions are basically doing the same thing, so they take the same amount of time. So if 1 million calls of one function takes 600 milliseconds, 1 million calls of two functions takes twice it, right? But the magic is here. If I put the static keyword to do method caching, basically I save a huge amount of time because these expressions get only executed once. So instead of 2 million times executing, basically 1 million times executing each line of these codes, 4 lines of codes, we only execute them only once. So it's a comparison between 4 execution and 4 million execution. So this is a huge amount of saving. So if I compile this and copy and paste it to the Java again, and then run our, so previously we got 1200 millisecond, and let's see how much it takes now. 244. Let's run it one more time. 250. So 250 millisecond. And again, it's a difference between 4 million execution of those 4 expression between compared to 4 execution. So this is more or less a factor of 5 saving, right? So this is very important to understand that it's better when we are dealing with this reflection type access to the fields or methods. It's better to cache them. When we define them, we also assign them. So this is initialization, and because we're using the static, it's going to be cached and executed only once. But there's also another way. If the person has like many, let's say 20 fields, and in each of these functions we have to get access to all of those 20 fields, then it becomes cumbersome to copy and paste all these and put them as a static in each function. So what we do, we define them in a global way right here outside the function, and then cache them basically in a separate function. And basically this is the topic of the next lecture. So I hope you enjoyed this video. Please stay tuned, and I'll see you in the next one.